and we are slowly moving on to discuss the gravitational field. I couldn't pass by this most beautiful thing. Look. I'm not quite sure what will come of this because it's quite windy today and the road is humming loudly in the background, but I hope it will be decent.
So, my friends, we continue the segment Simple Concepts, and today we are talking about something like the gravitational field. Right? This is not the simplest concept that could be chosen, but nonetheless, in all our more, let's say, extended, more comprehensive videos, the understanding or lack of understanding of the gravitational field often appears. Therefore, forming at least a general idea of what a gravitational field is incredibly important. Well, as before, my name is Yuri, and we move on to the main, essentially, topic of our episode. In general, the concept of a field in physics always makes you want to compare it with something. And almost always such a comparison will be completely incorrect. The thing is, when we look for some simple physical and material analogies, these material analogies become, well, let's say, excessively overrated comparisons. It sounds, of course, very daunting on one hand. On the other hand, it is completely incorrect to imagine any physical field as, for example, some kind of material cloud consisting of particles. This is a completely different concept. And it is appropriate to say here that any physical field is more of a mathematical concept rather than a physical one. And what we usually imagine as a field is more likely certain types of matter. Here is why. In fact, I immediately said that the video leans more towards complex concepts of physics. We cannot come up with a simple analogy, and we cannot say that the field is not a substance. Why was the idea of a field needed at all? In the course of research, it turned out that certain physical phenomena are not transmitted directly. Because for them to be transmitted directly, well, let's say a certain medium is needed. Imagine that you have a set of balls, and in order to push the far ball, you need to use some nearby object, whether it's a cue for striking or another ball used in billiards. This, I don't know what it's properly called, a cluster of balls. At some point, such things were described through the ether. And the ether is a whole separate matter. We won't start on it either, because it smells like, well, let's say a long argument. An argument without any basis. And some will say that ether exists, while others will say that it doesn't. In my opinion, the concept of ether was precisely replaced by physical fields. Physical fields? This was a necessary concept that allowed for the description of the transmission of a particular interaction. And so, essentially, we are getting even closer to the designated topic. It is logical to assume that if a field is a certain special type of matter, by the way, in textbooks this is usually how it is described, then in the case of a gravitational field, it is precisely a special type of matter that is necessary for gravitational interaction to be transmitted from one object to another. Well, and we remember that gravity arises where there are massive bodies. If we have a massive body, then there is a gravitational field around it. So, precisely using examples of gravity, it is probably easiest to understand why a field is not some special matter in the literal sense of the word. It is not something material, consisting of particles that resemble little balls, but rather a special kind of matter that differs from the matter we are accustomed to. We remember that modern concepts describe gravity as a specific phenomenon related to the deformation of space-time. This idea was proposed by Einstein, and before Einstein, similar logic was developed by other well-known physicists. But it was with the advent of the theory of relativity that a formal and, let's say, comprehensive description of gravity emerged. Today, gravity is described in exactly this way. Moreover, there are various confirmations that indeed suggest that Einstein's logic was correct. And so what exactly is gravity for us? It is the distortion of space-time caused by the presence of a massive body. The distortion does not occur because the massive body falls into some special space. Very often, a fabric is depicted with a squash, an orange, or anything else placed on it, forming a funnel, and it is said that this is gravity. No, in reality, the issue is much more complex than it seems. So, a gravitational field is where gravity acts. Imagine that you have two material bodies. They are massive. These massive bodies at some distance from each other will inevitably influence each other with their gravity. This follows from the well-known law, which Einstein did not abolish, where we have the gravitational constant multiplied by the mass and divided by the square of the distance between them. Accordingly, it is logical to assume that if we have moved far away to some distant galaxy, then most likely there are no massive bodies nearby, and gravity will practically not affect the body there. And here's an interesting point. The distance at which gravity affects an object is precisely determined by the range of the gravitational field. But despite all this, as we have already said, a gravitational field is not some special state of matter, which resembles a rain cloud or spilled paint or anything else. Or like scattered dust, any pleasant comparison you can think of, but it is a specific behavior of spaces. And here we take that very model that is depicted. By the way, it is correct. It is incorrect to only imagine that our gravity is this immersion, these funnels. Our very space is formed in such a shape. And I already mentioned that this is a separate story. And here is this comparison. It fits very well. When we have guiding spaces, when we have this lined scheme that you saw, when we have this grid, and it deforms essentially the dent that forms, this is the propagation of the gravitational field. Once again, I won't tire of drawing your attention to the fact that the dent itself is not the immersion, that's of an object with mass into this field. It is the specific formation of space-time itself around this object. This is a subtle and important point. But the fact that the object has thus formed space-time around itself indicates that there is a gravitational field around it. And from this example follows something else very important. It turns out that the gravitational field is a certain continuous substance that has, well, let's say a certain intensity, if it's appropriate to use this word here, near massive objects. It turns out that we have a gravitational field, absolutely everywhere. The gravitational field passes through any objects, and the gravitational field has a certain numerical characteristic. At the points where there is a massive object, and near it, the gravitational field has a non-zero value. And this non-zero value is expressed in this form. Here are the distortions. And at the points where, accordingly, matter is far away, this distortion is practically imperceptible. This is precisely, at the area, we try to imagine as a certain zone where there exists that very jelly, smoke, steam, anything, whatever you imagine in a material equivalent. Any physical field. By the way, wait, when you try to imagine that the gravitational field, specifically, is material and consists of some tangible and detectable particles, you are embarking on the path of searching for the graviton. And what is a graviton? It is the quantum of the gravitational field. It is the particle that, according to some physicists, is the means of transmitting gravity. Well, if you want to describe the gravitational field more accurately, more scientifically, then, in principle, it's better to use some mathematical logic and say that the gravitational field is a certain model that describes the state of space. And thus allows you to correlate with the actions of gravity at a specific point on a massive object placed in this space.